Hi, my name is Stephen Guerin. I'm here in Santa Fe with Paige, and I'm at Redfish Group, which is an agent-based modeling and data visualization company. We also have a little spin-out called SimTable for taking simulations and agent-based models that you're learning in Project Guts, but then using it for real-world problem solving for firefighters and emergency responders. So, taking those techniques that you're learning and applying them to the real world. So this starts off with next to me is a little sandbox, and if we can also hit that other light. Here we go. There you go. And I'll turn this light off here. So firefighters train in sand tables, and what we have here is sand. And think of taking your net logo or star logo model, and the sand or the height of the sand is your elevation. So here I'm taking a laser pointer in my hand, and I can come in here and put on an interface. Maybe I'll bring in, say, a web map here, and I can pan this map around like this. Again, this is just sand, and we sculpt it to match the elevation, which we have as a layer that we can bring into our agent-based modeling program, which we call AgentScript. So everything you see here is in a browser, and we're projecting it down and having a camera up with the projector watching the surface so we can make it interactive. And so let me turn off the elevation. And over here are some of the modes I can be in. I'll put it into fire mode and speed up time here, and I'll close that guy. And now we can set the wind over in this area and then start a fire down in El Dorado and see how that fire is going to spread. So if you think of this in net logo or star logo where we have patches, and the flame is, if you look at the fire model in net logo, it's very similar to that, where it wants to spread into its neighboring patch with a biased probability to go uphill and downwind. This is a way of sharing agent-based models out onto a physical table for firefighters and emergency managers. We can also slow down time here and then start looking at tactics, like if we wanted to say, how are we going to put out this fire? Maybe where are we going to put our bulldozers as we try to contain the right flank of this fire or the left flank of the fire? And then so this dozer is going to start to dig some line. And we can put down airplanes and things like that as well. I'll put an airplane up here, and that's going to try to drop some retardant or that'll slow down the fire. Other things that we can put on here. So if you think of modeling fire or flood or hazmat plume, so we're going to put, basically think, before we just did a fire, but now we're going to do turtles as hazardous materials that are going to do a random walk, that are going to be biased to go downhill if they're heavier than air. So we have like a vapor density. So I'll load up a particular chemical like chlorine gas, and we can then do a release at this point and see how that is going to spread over time as I change the wind, right? So I'll speed up time, and we'll see where that hazmat plume is going to go as I change the wind. Other things that we can put on here then would be, think about taking turtles and lynx and putting them together to make roads, and then putting turtles on the road. So we're going out to open street maps and bringing in data like here for this area. And then we have the lanes and the speed limits for any of the roads. And then I can just put cars down on here as walkers that are following the links, right? So as I put more cars down, let me turn on the car layer here. And I'll slow down time. So you can see those guys moving around. So I know the webcam is kind of a low resolution, but you should be able to see some cars moving around here. And then how do we set up evacuation routes for public safety and that kind of thing. You can also see, if we look up, just to pan a little bit up there so we can see both. Yeah, well, that's good enough. But wherever I click on the screen on my table, I can fly to that position in Google Earth. So that's like a second view. That's fine there. And what I'll show here too is the idea of in education, start thinking about how, and these are all just browsers that we're bringing up. If you pan up a little bit there, think of you using a QR reader so that somebody can join in on a scenario. So we're going to come in here and grab that QR code, and now we're going to load that URL in our browser, and run and kind of join this scenario. And then if you pan back down over here, I'll close that guy back up. Then you'll see on here on my phone, I'll go ahead and change the wind, and it'll be changing the wind on my simulation or things like that. So how can we use JavaScript and HTML5 to make a seamless kind of agent-based modeling and education platform, right? So that's kind of something to show you on the table. Oh, you might wonder kind of how we sculpt the sand. So we can bring in, say, the elevation layers or a topographic map and sculpt to it. And this can work as a scanner as well that tells us how high the sand is. So you can make arbitrary surfaces, right? So let's now pop over. I'll go ahead and screen share my computer here, over here, and share my screen. I'll just show you a couple of things here. This is one of our colleagues, Josh Thorpe. This is an example of running a flocking model that you're learning in class, or things like so we're looking at agents with areas of attraction and repulsion, or building up to an ant model where we're looking at how ants find food using pheromones. So think of these as kind of basic models that then we put into these real-world physical models. So for example, taking or traffic models. So here we are in Santa Fe, and we're going to fly through what's called Fort Marcy Park, where we basically burn a 50-foot puppet in effigy. He's called Zozobra. In Spanish, Old Spanish, it's Old Man Gloom. So we put in our report cards and our past test scores and parking tickets, and we burn them to get rid of the gloom. Divorce papers, yeah. But middle school, you don't have to worry about that stuff. In the future, that'll all be resolved. So think about how you get people off of this field and we're going to run a net logo model, and we're very concerned about these bridges here. And if you think about crowd dynamics, where if people are at 4 people per square meter, which is just really shoulder to shoulder, if you look at a meter on the floor and put 4 people in there, that's not that dense. But that would put 50,000 pounds on these bridges when they're rated only for 10,000 pounds. So we're looking at those kinds of issues. So here's a net logo model where we bring in the area and then just do a basic simulation where agents are following gradients out to the exits. So this might be an argument for, just so that people are aware of different exits, make sure we have ticketing on this area over here. So looking at different situations. We scaled that up, taking in open source tools like Blender, and we modeled PNC Stadium in Pittsburgh, doing basically a homeland security. How do you evacuate people safely? I'm from Cleveland, so we got to pick the stadium. So we picked Pittsburgh Stadium here, and we're putting some. Here's some disturbances out in maybe left near third base. Home base is here, or out in the outfield. And how do you make it safer for people to evacuate? And if you think of the outfield in a baseball stadium, how do you make it easier for people to evacuate out onto the field if necessary? So maybe making those outfield fences collapse. So what's the value when they have to put kind of a retrofitted stadium? How much safer can they make it, right? So these kind of questions of how to apply agent-based modeling for kind of decision making. In the fire world, this is how we started off simulating cars in Santa Fe. The esteemed Santa Fe Institute is about up at the top of the screen here. This is Gonzales Road, and this is the upper watershed here. And we're just looking at a fire model. So think about coupling 2 complex systems models here. So a fire model, which is kind of a patch spreading model, and agents moving on links, right? And then how do those interact? So we've also worked with, applying this to looking at watershed modeling of how water spreads on and what is a watershed. That's a nice kind of project in the 3rd grade level. Or kind of looking for ridge lines on a topographic map. So, making your patch values land elevation values and then running turtles on them. I think there's a lot of geo type of simulations you can do for ecological modeling and kind of, kind of sustainability and STEM kind of contexts. Here was, in New Mexico, we have the supercomputing challenge in high school and for middle schoolers. And some examples of like using agent-based modeling for doing machine vision. So if you think of the pixels of the camera as a value that you put into the patches, and then using turtles to find things like edges and finding blobs and things like that. Or in the 12th grade, one of our students was looking at dengue fever down in Cuba. So taking in the elevation, figuring out where the water would collect, because that's going to be the breeding ground for mosquitoes. And they're carrying the virus. And then looking at the density of the populations and having some probability of people moving between the big cities in Cuba. And then, so what would an epidemic look like? That's a little bit more spatially explicit than what you might do with just a big box. So bringing in real world maps and trying to get real world behavior a little bit better, right? So those are some of the things we're working on. What kind of spawned the sand table is when people do. They call these simulations too, but it's people doing planning around. And even though computers aren't involved, they're simulating a scenario. So when we saw them doing this kind of work, we saw it very valuable that they had a table in front of them. And sometimes they have a sand table that looks like this. And when we think about human-computer interaction, when we look at a table like this, at first it looks primitive compared to having a fancy touch screen or a phone interface. But when you think about people working together around a table, this is a very tangible way that anyone can reach out and change the wind or make a road or put a fire truck down instead of having to navigate crazy menus and things like that. So we're thinking about all surfaces in the room becoming projectable and interactive. So instead of having iPad screens everywhere, projection and cameras will make all surfaces in the room interactive. So here's some examples of firefighters sculpting their land up in Colorado, and they're using the colors of the rainbow to do that with red. And then they're going to use a laser pointer and bring in the satellite view. So while the interface is kind of maybe unique, I think the skills that you're learning in agent-based modeling directly map to this. So if you can think about making water fall downhill or fire go uphill, it doesn't take too much to make these kind of complex simulations with very simple rules. So I'll pause, see if there's kind of some questions.
Stephen, can you tell us how you got started on this trajectory? Is this something that you encountered within during your own education, or has this all been developed more recently?
So I started off in school in economics, and I was kind of attracted in economics to microeconomics, which you can start to think about agents and how they interact to make a larger system. And then I was also interested in graduate school in cognitive science, and from the same kind of perspective of how do neurons come together to make mind, but mind can also be much more extended as you get into complex systems. If you think of like an ant colony, where the agents or the ants themselves are like neurons, but the colony itself is processing information of where where the food sources are and the best ways to get there. I kind of came through a circuitous path. I kind of grew up with it. When I graduated from college, the internet the web anyway was kind of new, and how do you program distributed web systems? And that kind of got me interested in complexity, because as things scale up, I think there's instead of making these very static, in science we say reified, where you take something and make it something that's very dynamic and make it very kind of too concrete. I think a lot of information systems were designed that way. So I was very much attracted to the kind of the Santa Fe approach of designing systems. And I think if real world systems need to scale, they kind of have to take some of these approaches.
Okay. Another question. What is your vision for how this kind of modeling and simulation can be integrated during a school day? Do you see it as part of regular school day classes as they exist, or do you see maybe a change to the structure of the school day and the types of projects kids do to integrate this work?
Yeah, I think as the tools improve for modeling, my hope would be, well, the observation I have is when you get out of when you're in like graduate school, you start to realize that everything you've been learning since middle school is a model. Prior to that, I thought I was learning facts, right? So, but everything's a model, and models have limitations and they have strengths. And so I think if we can get modeling down to the 5th and 6th grade level and 7th grade level, where you show kids come across a phenomenon or a phenomena, and then they have the ability to try to say, well, how would I model that before they see what someone else thought about how to model it, and then they can see someone else's model of how maybe a spring works or how water flows downhill and makes rivers. But then they can, I think, having the ability to write their own models and test them. But I also think with projection out into the classroom and making it very physically tangible to interact, say, putting down a salt and pepper shaker and seeing a charge field between them, if this is a positive charge and a negative charge. So I think we can make models a lot more tangible for students. And I think the scripting is going to come along where it's going to be, as you're already seeing in the tools you guys are using, more composable with blocks. We don't necessarily have to go down to scripts. As students are very good at making very complicated structures in Minecraft, scientific models are about as complicated as that. When you look under the hood, there's not that much going on beyond what a more complicated Minecraft model is built out of, right? So I hope modeling goes way down, and there's a language of students. So like they get language like spreading activation. So a fire model is a spreading activation model in the same way that a virus is a spreading activation model, in the same way that a rumor, so that they start to get a language that they communicate with each other to say spreading activation, and they don't have to describe the specifics of their particular domain. They can communicate with another scientist in another discipline and saying that's the dynamics in my world, and they can share some ideas. Just as how ants find food is exactly the same model as how lightning discharges to the ground. So they can talk about, so an ant person can talk to a plasma physicist and have a meaningful conversation about their models. In the way that 20 years ago, someone would say, my model has a 1/x relationship, and that you don't care what x is, you already know what that curve looks like. We think there's going to be a language of modeling, and that's going to be very important to build up science, and students are going to be on that vanguard of developing that new vocabulary.
Fantastic.
Well, so this is Paige here. So what do you think, like if these kids are exposed at an early age, let's say upper elementary, middle school, to these concepts, what do you think, like how does that change their perspective on seeing the world?
Mitch Resnick captures this very well. I think if before you're exposed to these kinds of models, you tend to think of this centralized controller, right? And so I think as you get more and more familiar with it, as you see a system out in the real world, you can start to guess at maybe what is the distributed approach that this is solving a problem. And I think so it becomes a natural way of, it's a lens that you put it as you look at the world and how do you making sense of the world and how do you think it works. I think it's very important to have this distributed notion.
What are the resources out there for a teacher that has never done this before? Do you have any suggestions on that?
So I think there's just in these last 2 years, there's an explosion of teaching computer science skills out there, and I think that's going to very much, it's going to feed on itself and accelerate. So prior to, even just 2 years ago, I think there was this kind of a frustrating process where you had to go out, download code, pull it up over here, try to run it, compile it, and then get it out there. So I think, so there's sites already for teaching code, and I think this MOOC is an example of one in code.org. But I think it's going to get even better where you're able to go in and have that shared session with a mentor or an expert that's going to help you to work on your model as well in real time.
So I think, David, you were raising your hand. Do you want to unmute?
There we go. Hey, Stephen.
Hey, David.
Have you heard of the augmented reality sandbox that the Keck Center developed over at UC Davis?
Sure. Yeah. Using the Kinect?
Yeah, using the Kinect thing. I just put a link to it. So we've been building one and playing with it, and it's great fun. My focus as a geologist, working with the students, getting them to understand the abstract nature of topography for an 8th grader, it's really been very beneficial, and they're fascinated with it.
Yes.
Your program would be a obvious move forward from the augmented sandbox in terms of now you actually are showing an application of essentially the same sort of thing.
Right.
Is your software available?
We are making, there will be a free version, and we're making it we're trying to minimize the hardware requirement for students as well. So we will be making a free version that uses the camera on a smartphone and a projector. They could even run it from a phone driving the table, or if they plug a laptop into a projector. Or it can run off of a $40 webcam. So instead of using, so the Kinect works by putting out infrared light, but our kind of feeling is you already have projection light to play with, so you're using light to measure, and so we think it's kind of redundant to use the Kinect. There's advantages of real-time processing with the Kinect, but we think we can do real-time with just a camera and a projector too, and trying to bring the cost down.
Yeah, it would certainly be easy to integrate based upon the current format of the augmented sandbox, your program into the same setup, since it is just a sandbox and you're just throwing the image on the sandbox. It would just be really cool to have that program and to run it, because I think, even still as it is right now, I'll show your presentation to my students probably within the next week to say, look, this is the reason why we're playing around in sand. Like there is an application to this whole thing. And that's the most important thing, is they're learning these concepts, seeing a model of it, but now like, hey, look, firefighters are actually out there using this thing in Colorado, seeing this thing and playing with scenarios. The whole reason why we did it was so that we could model and play with alternatives to the massive Colorado floods that just occurred a while ago.
Right, up in Boulder, yeah.
Correct. And that's where I am, is in Boulder.
Right, and the Boulder fire, there's a group up there that has a sand table, a sim table in Boulder.